Today, almost a century after Bauhaus, we have started an unprecedented attempt for design for the extraordinary, life. Now in the 21st century, demand for design for the extraordinary is increasing at a remarkable rate. Design for the extraordinary is artifact design for use under extraordinary mechanical constraints. For example, the design of deep-sea submergence vehicles, or micro-robots that operate in blood vessels. Can someone design an appropriate artifact for the extraordinary? Life, one of the keywords of the 21st century, is the subject for this design for the extraordinary. At present, many advanced research institutions and scientists all over the world have shifted their interests to fields more related to life, such as biology, medicine, and welfare. Research of artifacts and systems related to life will be the main focus of the 21st century. Therefore, design for life will undoubtedly become one of the main subjects for design. Are conventional design methods applicable in such situations? In the past, design has mainly been divided into two types: design that originated in Bauhaus, and engineering design that has shown remarkable progress during the latter half of the century. However, neither can fulfill what is required of design for life. When designing for the extraordinary, life is required. It is a challenging quest to come up with and evaluate adequate design solutions using existing design methods. Design for life is difficult from both design and engineering viewpoints, and is in itself another type of design. We are now facing a new design phase, and must pace towards another type of design. To confront design for life and another type of design, the Keio Advanced Design School, course of Product and System Design, started this new program. Two important issues have been focused on in the approach. 1. Obtaining scientific and engineered knowledge through classification of the extraordinary. 2. Total design from multi-aspect viewpoints, taking advantage of the knowledge obtained. To achieve the intended objective, designer must participate from stages of fundamental research with scientists and engineers, which we call design and fundamental research. Unlike the conventional process, in which the design is based on existing technology, this type of collaborative design will help explore design from foundation technology to fundamental system development to a more global perspective. In this way, the school aims to create new values. In order to design for life, we have set two methodological viewpoints: biologically inspired design and interaction of life systems and artifact systems. Biologically inspired design, we propose, not only intends to mimic the form and structure of living creatures, but also the biological system itself, from emergence to sustainment. Autonomy, cooperativeness, and hierarchy are some of the significant features of biological systems. By learning from these characteristics, the school aims for intrinsic imitation of life. Integration of life systems and artifact systems refers to total design including biological systems, while existing design tends to stay bound to predetermined restraints of artifacts. When considering humans and other living creatures in the design process, conventional design methods have, in many cases, considered these to be another of the many constraints. However, as can be seen lately in the fields of tissue engineering, in cases such as regenerating tissue on artifacts, and life cycle design taking advantage of degradability of microorganisms, some systems demand total system design, specifically integrating artifact systems and life systems. Our design school adopts the idea of such integrated systems in proceeding with design. 3 project themes related to design for life were taken up, applying currently developing technologies at Keio University. We proposed BIMUS, a biologically inspired medical operation system. Many medical operation systems today are almost totally dependent on the needs of the surgeon and existing technologies. We proposed a novel system focusing on the interaction of a surgical system and hierarchy of technical systems. Interaction is a major feature of biological systems, and integrating interaction and hierarchy is critical in formalizing a novel medical operation system. This is the flow of the whole system. The main features are concerted medical service through informed consent and simulation-based laparoscopic surgery. As for the informed consent, at present, the patient is not fed enough comprehensible information, thus unable to actively participate in choosing the treatment. Our system explores ways for concerted medical service, in which the patient can make their own decisions with the support of doctors. The patient will be provided with easy-to-follow information through 3-dimensional modeling, use of database, and large LCD screens. Simulation-based laparoscopic surgery. Laparoscopic surgery requires extremely high technical skills, and lack of experience can lead to fatal accidents. BIMUS allows the doctor to train and practice through simulation, using information obtained from past surgeries and 3D modeling of the human body. With enough time to prepare for a surgery, reliability of the whole system will greatly improve. The hierarchical design modeling method, a technology still under development at Keio University, was implemented in designing the proposed surgical robot. Other technologies such as the master-slave combined manipulator and effectors using multi-DOF ultrasonic motors are also some of the new technologies introduced. Simulation and surgery will be conducted, taking advantage of these developing technologies, and will lead to producing new values. This group proposed a novel surgical system, BIMUS, a biologically inspired medical operation system, integrating the interaction of surgical systems and the hierarchy of technical systems. Our work is on a life support vehicle for 2. We propose a traveling vehicle, life support vehicle, for the elderly and challenged people. We set out to make their lives more active and satisfactory. We designed a vehicle car that supports the journey, and a vehicle chair that supports activity at the destination. In designing the vehicle, we were inspired by creatures that bring up their infants in their mouths. The vehicle is composed of 3 systems. The 3 systems include a riding system, comfort system, and driving system. With 3 systems, we developed a life support vehicle for 2, through collaboration between the vehicle car and vehicle chair. These are the exterior and interior design of the proposed vehicle car. In designing the vehicle car, we use the shape design method using macroscopic shape information. That is a digital design method under development at Keio University. This method helps create ideas of shapes easily. Using this method, we propose a way of styling a life support vehicle. Next, this is the design of the vehicle chair. In the vehicle car system, the person rides on a wheelchair and can drive the car remaining seated on the wheelchair. The difficulty of getting on and off the car is eased by making the front and the rear open. The driver may get on the vehicle from the rear and get off from the front. To handle a vehicle car in the same way as handling a wheelchair, we applied a by-wire system. When handling a wheelchair, vibration greatly affects comfort. Therefore, our system makes use of an active vibration control system, which is also currently being developed at Keio University. In addition, we propose the structure of rotating seats for the vehicle car, which is suitable for the concept of life support vehicle for two. We also propose a broken structure, a seat swing structure, and a pressure distribution structure to reduce fatigue and to make time more relaxing for the two people on long-distance journeys. Future issues would be the verification of effectiveness when using a combination of these technologies. This picture shows the vehicle car and vehicle chair in use under the concept of life support vehicle for two. As you can see from the picture, using this vehicle car, you can travel to places where you could never visit in daily life, and you can share time with your partner on a vehicle chair at your destination. Our project is on artificial joint system interacting with organisms. We would like to propose an innovative artificial joint system under the concept of interaction between implant and organisms, viewing artificial objects and organisms from multi-aspects and an integrated point of view. In designing conventional artificial joint systems, the factor of organisms has been considered constraints, and we need to evaluate whether the implanted materials satisfy the constraints. However, in our system, the material interacts with the organism and external devices, and the constraints such as the surrounding environment can be eased. To realize our concept, we needed to add the organism as a component in the solution space, and to map from the meaning space to the solution space. As a result, the organism becomes one of the variables in designing the system. The hip joint is the subject of the system. First, we organized hierarchical meaning components necessary for an artificial hip joint using QFD and ISM. In addition, we found the technologies from a macro, meso, and micro scale point of view, and introduced them into the proposed system. From a macroscopic aspect, we propose supporting tights for recovering athletic ability and reducing motion restrictions of patients after operation. This actuator-embedded supporter works synchronously with the motion of the human body, and we expect that it can be worn for some time after the operation. From a meso aspect, we propose a fluid injection system to improve tribology characteristics of the sliding part that substitutes lubricated body fluid of conventional devices, reducing wear of the joint. We also propose an optimized stem form using emergent form generation system. Emergent form generation system consists of a generation process and an optimization process. In the generation process, induction and apical dominance, two properties of organisms, are imitated to generate diverse forms in a self-organizing manner. Here is the process of form generation. In the optimization process, forms are optimized, while maintaining the diversity and features of the forms obtained in the generation process. The results show that the system can obtain diverse topological structures. These figures show examples of design ideas. The results show that unprecedented stem forms were obtained by the proposed system. From a microscopic aspect, the stem surface is subjected to fine particle bombardment, FPB treatment. FPB treatment is a newly developed surface modification process in which fine particles are bombarded to the surface with very high velocity, creating microtexture on the treated surface. In conclusion, we proposed an artificial joint system that improves the quality of life of patients with fine biocompatibility and reliability. by realizing a new meaning of interaction between implant and organisms. Our Advanced Design School was a 4-month activity from April to July 2004. This was an unprecedented attempt, and the accomplishments are yet to be concluded. However, we believe the continuance of the school is of paramount importance in order to design for the extraordinary. Life is another type of design.
授業参加して真面目な話、このデザインのデザイン分野に入るきっかけになれたかなって。こんなことやってるけど、こんな楽しい面もあり、結構学校に慶応に来た面もあり、忙し楽しかったです。新しい発見いろいろありました。今まで機械しかやってなかったので、デザインとか未体験のゾーンでしたけど、いろんな人にも出会いましたし、渡辺先生もいかついですし、楽しかったです。
そうですね、楽しかった反面すごく辛かった。でもみんなで楽しくやることができたので良かったと思います。
自分の研究以外のことをいろいろ学べて、いろいろ発見するところもあったと思います。
まず本当に楽しかったです。それと、結構辛かったんですけど、毎週その辛さを超える楽しみがあったので、結局今まで続いてしまいました。新しい発見はそうですね、なかなかこれだけデザイナーさんに直接話を聞く機会とかもないので、そういう経験も楽しかったですし、あと同じデザインが好きな人たちといろんな話ができたのもとても良かったと思います。松岡先生にこの授業に呼んでいただいて、はるばる東大から参加させていただいたんですけども、こんな貴重な機会を作ってくれた先生にどうもありがとうございました。